Hello guys, so welcome to this lecture. In this video, I'm going to prove a theorem, actually a lemma emanating from the proof of the Picard-Lindelof Theorem. And then what I'm going to do is we'll do an example of how you apply these error estimates of the Picard-Lindelof Theorem. So here I'm going to repeat the theorem here just to keep us abreast with the conditions of the theorem. F of xy is to be continuous in a closed rectangle and therefore is bounded by some m. F of x has to satisfy uniform Lipschitz condition, which is given by this. Y naught of x is our initial guess, which has to be continuous in the rectangle. Once these are satisfied, then we have a unique solution of the IVP given by this. Okay, and this solution is valid in this interval. Okay, so one important thing about proofs is that the proofs can often lead you to some important results. Okay, if you like, bonuses from the proof. Okay, so this seems to be the case here. So here's a lemma that's going to help us to find estimates of errors that we make by taking successive estimates, if you like. Okay, I will explain a bit more about that. This is the lemma for the conditions in theorem 14. Theorem 14 is just the Picard-Lindelof theorem. For all x in the interval I, then the following error estimate holds. The difference between your actual solution, right, and your estimate is not more than this here. It's less than or equal to this, okay, where the maximum of this, the difference between y1 and y0 is less than some positive number n, right, in the interval. Okay, so why is this important? Now, this is important because you can't always find an exact analytic solution to the IVP, but you can find an estimate, if you like, using, let's say, Picard iterative procedure. So suppose that you're able to find that estimate and you don't know the actual solution, which is this. This tells you that once I know whatever is on the right-hand side here, I know the difference in absolute terms between my estimate and the actual solution, even though I don't have the actual solution. Once I know what is here, I can tell you that my solution or my error should not be more than this quantity here, which is given by this. So that is why it is important. Of course, if you know the actual solution and that it exists in some interval, of course you go with that. But this is the case where sometimes you don't have the actual solution, and so it becomes difficult to find out how accurate your approximate solution is. So this is a way to help you to have a handle on that. All right, it can be crude as we see in the example, but of course it helps you to have some idea of the error you make by using this estimate instead of the actual solution. Okay, so to prove this, we have to recall this, right? This inequality that I mentioned that is important. We'll be using it again, so I just rewrote it here so that we can refer to it. Now, we're going to start from here. For n greater than m, we can use the triangle inequality, right, to show that the absolute value of y n of x minus y m of x, right, is less than or equal to this. Okay, I mean, you can easily show this by expanding, right? You know the trick you often do in analysis, right? You can do yn minus some stuff in between m and n, some functions minus ym. Then when you take the absolute value of that, you can split them into pairs, right? And then the absolute value of your bigger thing has to be less than or equal to that of those individual terms. So that is what is happening here. I mean, you can try this for some values of m and n and see that this is true. Okay. So this is less than or equal to that, but remember the inequality says that this absolute value here is less than here. This guy here is less than or equal to this. So if you replace m with I think k plus 1, you should get you should get this, right? So you can plug it in and you have this is less than equal to that. But once again, we know that the absolute value of x minus x naught is less than or equal to h. So that gives us this. All right, good. Now note that we are summing from k equals m to n minus 1. All right. Now we want to sum from k equals 0. So you can use, the trick for series, if you remember series and sequence in calculus, you can change the index to start from 0 instead of m. When you do that, you're going to get this expression here, this thing here, where you can pull out your n lm to the power m. Now k will start from 0 to n minus 1, and you're going to have your denominator, numerator is the same. The denominator now becomes m plus k factorial because we made these changes here, right? Remember, you bring m here, call it some p, and then later on you change it back to p. Well, this is calculus, right? You can do that. So when you change the index to start from 0, you're going to get this expression here. Okay, good. Now, this is like this multiplied by 1 over m plus k factorial. But 1 over m plus k factorial is less than or equal to 1 over m factorial k factorial. So you're going to use this inequality here. So when we plug it in, we're going to have the absolute value of the difference here should be less than or equal to this quantity here, okay, where I pull the m factorial out, all right, and now we are summing over k's given by this. Good. Note that if the upper limit of the sum here is infinity, then of course k from 0 to infinity will just give us the exponential of LH, right? So you're going to take the limit as n goes to infinity. Take n to infinity. So as n goes to infinity, note that if n is going to infinity, these guys approximate, right? They converge to y of x. So as n goes to infinity, this guy becomes y of x. This is going to infinity, so this guy becomes e to the power LH. So that is what we have here. All right. So as n goes to infinity, this guy becomes y of x. This still remains as that, and this is less than or equal to this expression, which is given by this. Okay. So if you like, this is one estimate that gives us, that this is one expression that gives us a bound on the error we make, right? This is the actual solution. This is an estimate. We are saying that the absolute value of the difference has to be less than or equal to this. So this is one part. We'll get another one, all right, and to fulfill this condition here. See, this is the minimum of this. So to get this, we need another estimate, okay? Now, the other estimate we can get from the inequality 5. Inequality 5 is this one. From this inequality, all right, we can actually get another estimate, right? If you let n go to infinity. So let's see how we do that. So I'm going to bring this over here. So that inequality that we just saw is this, right? But k is from m to n minus 1. Of course, then this has to be less than or equal to k from 0, right, to n minus 1. This has to be bigger because they're positive quantities, right? This has to be bigger because this is starting from 0 to n minus 1, whereas it's starting from m, where m is some positive number. Therefore, this is less than or equal to this. But once again, if n goes to infinity, this guy here, the summation thing becomes e to the power LH. So as n goes to infinity, we're going to have, this becomes y again. This is y underscore m. This is less than or equal to n e to the power LH. Okay. So we have two error estimates now. So we just combine them. We combine equation 8 and then 7, this guy. When you combine them, you're going to get the error estimate in the lemma. Okay, so yx minus ym is less than or equal to n e to the LH, the minimum value of this. Okay, so you take the minimum of this, and that will give you this error estimate. Okay, good. So that brings us to the end of the proof. We'll do an example to show how you apply this this error estimates to a differential equation, to an IVP. This would be an IVP that we know how to solve. And so it helps us to judge how good these error estimates are. So here I'm just repeating the theorem again, because to do the example, we have to make sure that we satisfy these conditions of the Picard-Lindelof theorem. So I just repeated them here for reference sake. Okay, so here it is, and then we'll go to the example. We want to consider the initial value problem, right? dy dx is equal to 1 plus y squared. Y at 0 is equal to 0. We can easily solve this to get a solution. Y of x is equal to tan x, right? Now, around 0, 0, right? When x is 0, y is 0, around this initial condition, this solution actually exists in the interval negative pi over 2 to pi over 2, right? You know the tan, right? Tan from negative pi over 2 to pi over 2, and then it goes that way. So we know the solution, and we know that it exists in this interval. What we want to do is that we want to use these error estimates, right, from the theorem to compare the error estimates and the interval given by the theorem to the actual interval that we know, and to see how good these error estimates from the theorem are. All right, the intervals are. Good. Now we can apply the theorem, theorem 14, right, to find the interval of validity and error bounds as follows. Okay. Actually, well, here the Picard-Lindelof theorem, or the lemma that we just showed for error estimates. That's what we're going to use. So first of all, you have to check that the conditions of the theorem are satisfied. Okay. So the function f here in this case is 1 plus y squared, and it's continuous in the rectangle, right? Absolute value of x less than or equal to a, absolute value of y is less than or equal to b. And then f, right? The absolute value of f is this guy. This is less than or equal to, I put in the max here. It has to be less than or equal to 1 plus b squared. Okay, so this guy here is now our m. So the big M in the theorem is 1 plus b squared. Okay, we'll work out what b is. A, we have an idea, right? A, we know that the solution exists between negative pi over 2 and pi over 2. So if you like, the max that A can take will be like pi over 2, right? But we'll leave it as A for now. Then the function f satisfies the Lipschitz condition, right? So we can easily show that. We've done this before. So take this minus that, which gives you this. This is equal to difference of 2 squares, so 1 plus 1. So I can take the max on the y, right, in the rectangle. Okay, the max is b. So I can plug in b and b. That gives me 2b multiplied by this. So my Lipschitz constant is actually L equals 2b. So I know that. So once I find what b is for my interval, I know L. Okay, so the first two conditions are satisfied. We have them here. It's a closed rectangle, so L here is a number. Okay, now the third condition is that we need to find some continuous function, if you like, the initial solution. All right, so we're going to use y equals 0, the initial condition that is given. So we'll let y naught of x to be equal to 0, which is continuous in the rectangle. Okay, which means that there exists a unique solution because all three conditions are satisfied. This is a unique solution of 10 in the interval. Now, from the theorem, the interval is that absolute value of x minus x naught, right? The x naught is 0, right, from the initial condition. So absolute value of x is less than h, where h is the minimum of a and b over m. Big M is 1 plus b squared. Big M is 1 plus b squared, right? So b over m is this. Great. So the conditions of the theorem are satisfied. That is the first thing we need to check. And then from there, we know the interval, which is given by this. However, right, we can show that this b over 1 plus b squared is actually less than or equal to 1 over 2. Okay? And the equality holds when b is equal to 1. All right? So this, if you like, this guy here is like a half. The maximum this can be is a half. which means that the optimum, right, the optimum interval which the theorem actually gives us is that the absolute value of x has to be less than or equal to half, right, because of this half. Remember a here, a is x minus x naught less than or equal to a. We know that the solution exists between negative pi over 2 and pi over 2. If we take a to be, let's say, pi over 2, for instance, pi over 2 is way greater than 1 over 2, right? So the minimum here has to be the half, which is this. Okay, so that is our h. Our h is 1 over 2, the h in the theorem. Good. Now, how do you show that this function or this expression here is bounded by a half? It's less than or equal to half. Well, you can take f of x to be equal to x over 1 plus x squared, right, as a function, and use the techniques of integration, or not integration, sorry, the techniques in calculus, right? How to find the minimum and maximum values of a function. Find the derivative equated to 0, get the critical points, and then you find where it is maximum, right? Now, if you do that, you see that this function, which I'm calling f of b here, this is maximum when b is equal to 1, and when b is 1, this is half. Okay, so it is maximum of half, so it cannot be greater than half. That is how we get this. So you can check it using calculus, the min max techniques in calculus. Okay, good. So just by these analysis, we see that the theorem, right, the lemma that gives us error estimate says that the solution actually exists between negative 1 over 2 and 1 over 2. Okay, which is really, really very restrictive. I will show a graph at the end of the talk, at the end of the, this lecture. Negative pi over 2 and pi over 2 is way wider than negative 1 over 2 to 1 over 2, right? So it's very restrictive. So this is actually very crude, or if you like, a rough estimate of the interval. The actual interval is actually wider than what the theorem is giving us. Okay. Great. So that is the comment here. Good. So now, how do we find the error, the bound? Note if you go back here, here, the estimate, the error that you make if you make estimate. So we're going to make some estimate, find some estimate using the Picard iterative procedure, find some estimate, and then check the difference between that estimate and the actual solution, and then find this bound, this error estimate. That's what we're going to do next. Okay. So here, so for the error bounds, we note that the Picard iterative scheme for 10 will take this form, right? If we go, 10 is this equation, right? So the f is 1 plus y squared. Good. So we know how to find the Picard iterates. We have y naught plus the integral of this. Y naught here is 0, so we end up with this. F is 1 plus y squared. All right, so that gives us this estimates. So we're going to put successive estimates in here. Here we can integrate 1, and that gives us x. Also note that we are integrating from 0 to x because our initial value is 0. Okay, so if you integrate 1, we'll get x here plus integral from 0 to x of this guy here. Good. So for m is 0, if you put m 0, this is 0, right? So we get x here. If m is 1, we're going to get y1 squared. y1 is x, so we're going to integrate x squared, or if you like, t squared. Okay, so you have x plus integral from 0 to x of t squared. When you do that, you get your y2, your second estimate, to be x plus 1 over 3x cubed. Okay, so you have a first estimate, which is as x, a linear function, and you have a second estimate, which is this. So we want to see how accurate, if you like, how accurate. What is the deviation between this estimate and the actual solution, which is tan x. All right, so that's what we're going to do. Now the error bound, right, from the lemma is given by this. Okay, so what we actually need to get the right hand side here is to find what our n is, what our L is. Remember, L is 2b. What H is. In this case, M is 2, right? We only did the estimates up to y2. So M is 2. So we need to find them, and then that will give us this this right-hand side of the error estimate. Okay. Of course, the marks of the difference between this and this is absolute value of x. We showed that the theory says that the absolute value of x has to be less than or equal to 1/2, and that is equal. That should be the n, right? From the lemma, this guy here is less than or equal to some n, right? But we showed that this is equal to this, and it's less than 1/2. Therefore, that has to be n. So we know n to be half. Okay. B is 1, right? B is where we get a maximum. So B is 1. H is also half, right? We found H is half, right? Absolute value of x is less than or equal to this. So H is half. L is 2B. B is 1, so L is 2. M is 2, as I said before. So if you plug those in here, N is going to be a half. L times H. L is 2. H is half. That gives us 1. So that gives me E, right? So I have 1/2E. Then the minimum of 1, and if you compute this, you get 1/2. The minimum of 1 and 1/2, of course, is half. So you get a half from here, multiplied by this half, you get 1/4E. So the difference between the actual solution, which is tan, and the estimate, which is x plus x cubed over 3, is actually equal to, is less than or equal to this. So it shouldn't be more than the error you make if you just estimate, if you just leave this as your solution. Suppose we take this as our solution, then what we are saying is that the error that we make should not be more than 1/4E. All right, for x lying in this interval. Okay, so it actually helps you. Note that we got here without using the actual solution. So I could actually have put like y of x here. I don't need to know the actual solution that it is tan x in order to get this. Okay, so even if I don't know the actual solution, I can still get this stuff, all right, from the analysis that we just did. And that will give me an idea of the error I make by using this x plus x cubed over 3 as my solution. Okay, now, so here's the plot I made, right? So you see that when you solve the solution explicitly, you'll find that your solution actually exists, right? Between -π/2 and π/2, right? These are not included, of course. It goes to infinity there, but it's quite wide, right? But the theorem actually says that the solution, right, exists between -1/2 and 1/2. So you see that it is quite crude, right? It doesn't even extend to 1. So it's very, very limited. The interval the theorem gives you is quite limited compared to the actual interval that you get by solving it. So of course, if you can solve the problem, then you solve it. If you can't, this gives you some estimate of the error you make. Okay, great. So the red is, of course, our estimate. The blue is the actual solution, which is tan. And this is a plot of that. Okay, so this is how you apply the error estimates to IVPs, so that if you don't have a solution, you can actually use them to do that. Okay, I'm going to end here, and then we would we'll continue later. I'll give you some exercises on this so that you have an idea of how to apply that. Okay, so all the best.